Hello and welcome back to our magic string lectures. Today I will finish part number 4 and we'll probably also have time to start with part 5, which will bring us back to the space-time perspective on string theory, and we will finally be able to explicitly construct physical states and identify them with elementary particles with a given mass and spin. The relevant example sheet for parts 3 and 4, the conformal field theory and worldsheet aspect part, is problem sheet or example sheet number 2, and I've posted the answers for the questions this morning. Part 5 I've also already put on the magic page this day, and there will be a third and final example sheet about materials that we are doing in part 5 when we talk about space-time aspects of string theory. Before we resume the lectures, some amusing remark on the side. This is the third Thursday in the month of November, which does not only have one, but in fact 2 special meanings. First of all, and I think this is by decree of the French wine producers, it is the World Beaujolais Nouveau Day, but thanks to the United Nations, it's also World Philosophy Day. So here's an idea for this evening. Let's have a glass of wine and some deep thoughts. And some inspiration of deep thoughts might come from us continuing the lecture. So I rewind a little bit. I think we left off at some point where we had a general discussion of operator product expansions. So to describe a conformal field theory, it's enough to know a complete set of local operators with definite scaling dimensions or scaling weights. And the OPEs are then in the structure fixed, or the functional depends on the distance between the operators fixed by the scaling dimensions, and the non-trivial information which characterizes a conformal field theory is then in the coefficients which tell us how the operators couple to each other. Good. Now, it's an important result which I have stated here in formula number 10. So ideally, we would only like to deal with primary fields, but the OPE between 2 primary fields does not only involve primary fields, but also descendants of these primary fields, which we discussed last time. Of course, the function depends on z minus w is still completely fixed by weights. That's not a problem. But a part of coefficients ci, j, k, which tell us how product of primaries expands into other primaries, we have also coefficients beta, which tell us how the various descendants of the primaries that we get come into the game. Now, it's an important result that these coefficients are not independent, but they're completely determined by the other data. So we only need to know the various conformal dimensions or conformal weights and the central charge. In summary, a conformal field theory is then determined by knowing the charge, knowing the weights or dimensions of the chiral primaries, and the coefficients which tell us which primaries appear in the product of 2 other primaries. Since primaries generate representations of the Virasoro algebra, these are analogous to the Clebsch-Gordon coefficients of angular momentum addition. These are group theoretical or algebraic coefficients which tell us how representations couple to each other. And this contains all the information about the CFT. Often, and in particular when we use this to construct the Hilbert space of a string theory, we want to have a conformal field theory which is unitary. That means the inner product between states is positive definite, and that means it's non-negative, and it can only be 0 if the state we are looking at is equal to 0. we can apply this to get some information. And let's take a highest weight state with some weight HA, take the nth descendant by applying the operator L minus M, and then look at the norm of the state. Using the Virasoro algebra, we can work this out. And then by imposing that this is non-negative, we can extract the following information. I leave it to you to spell out the details, but the information that we get is, firstly, the central charge. Oops, this looks ugly, so let me draw it again. Sometimes there's a bit of inertia when I draw here. So first information is central charge must be positive. This explains my previous remark that it is very essential to have a non-trivial unitary conformal field theory, that we have a non-zero value for C. With C equals to 0, we wouldn't have a non-trivial theory. We also learned something about the allowed weights. So the weights are non-negative, and they can only be all 0 for a unique state, which is the ground state. And if you look into it, you will find this is the SL2C vacuum that we discussed. This also explained why I defined conformal primaries as cotensors rather than tensors with respect to conformal transformations. Now, there is one phenomenon which we also will have to deal with when we look in detail into the Hilbert space of a string in a covariant quantization scheme. Namely, let's say we have a Verma module, that is the Virasoro representation created by a conformal primary. That will have descendants, but it might happen that there is a descendant which is not 0, so non-trivial vector, which is a descendant, but which is annihilated by all ln's with positive n. That means that the state is a descendant, but at the same time it's a primary state. But such states are also null vectors, meaning that they have 0 norm, and more generally, they're orthogonal to all states in the Verma module. And that it means including themselves, so in particular, they have a 0 norm. They're also called singular vectors. In this case, it's clear that the scalar product that we get is positive semi-definite rather than positive definite. And the same we will observe for the physical state space of a string. But since these null vectors are by themselves primaries, they create Verma modules which sit within our original Verma module, so they are Verma submodules, and we can obtain a positive definite scalar product by identifying any states which differ by a state which belongs to these Verma submodules. So put more simply, what we have to do in this situation, we identify any two states with one another which differ by such a null vector, and then on the resulting space we have positive definite scalar product, and many Hilbert spaces occur in this roundabout way. As an example, let's look for null states at level 1. We take a highest weight state of weight h. This is an eigenvector of L0 and annihilated by the ln's with positive n. Then we can compute the norm of the level 1 descendant. We write this as a scalar product. Then we use the property of the state h to replace this by the commutator. Then we can use the Virasoro algebra. And then we use this as an L0 eigenstate. And we see this state can only be 0 if the weight of the state is 0. For conformal field series with C larger than 1, this is the only null vector. And it belongs to the Verma module of the identity operator, if you want to place it. Now, slightly less trivial is to look at higher levels, and there's a systematic tool for doing this, which is called the Katz determinant. The Katz determinant is formed in the following way. We take all level n descendants of our primary, and then we take the matrix of all possible scalar products and the determinants thereof. This is the level n Katz determinant for the Verma module with created by primary with conformal weight H in a series with central charge C. And null states will then just correspond to the zeros of this determinant. So you have to compute this determinant and explicitly identify zeros. Here's an example for n equals to 2. The level 2 descendants are obtained by either applying L-2 or applying L-1 twice. This gives a 2 by 2 determinant. And by using the Virasoro algebra and eigenstate properties, we can work out this determinant. It gives us a cubic polynomial in H. One of the solutions is one that we already know, but we discover that potentially at level 2, we have 2 further values of H which can give us null states. This Katz determinant is an important tool in the classification of conformal field theories, in particular in the successful classification of conformal field theories with central charge smaller than 1. Good, this is a wide topic, so let me just make a few general comments on the classification of unitary conformal field theories. For C smaller than 1, unitarity allows only special quantized or discrete values of H and C. The corresponding series have been classified and form what is known as a minimal unitary series. So it's a single series of infinitely many series with central charges that start at 1/2 and then accumulate towards C equals to 1. Since the OPEs of primaries determine the CFT, it is important to note that these minimal models only have a finite number of primary fields that comes out of this analysis and classification. And in this sense, all theories in the series can be solved exactly because everything is determined by finitely many correlation functions, essentially the 3-point functions which evaluate the product between any 2 primaries, expanded again in primaries. These are the finitely many CIJKs, and once I have them in principle, I can compute everything else that I'm interested in. It turns out that in these series, the values of C and H are rational numbers, and therefore minimal models are examples of what is called rational conformal field series. But rational conformal field theory is a more general concept, which is important because if C is larger or equals to 1, then allowed values of C and H become continuous. And in general, we have an infinite number of primary fields. So there is no obvious way how we may classify or solve exactly such a series. However, it often happens that CFTs have additional symmetries. In particular, there can be so-called extended chiral algebras. This is an algebra existing either in the holomorphic or in the anti-holomorphic sector, when it is then called antichiral, which extend the Virasoro algebra. And then with respect to the full algebra by Virasoro times this extra algebra, it might happen that with respect to this larger algebra, we have a finite number of primary fields with respect to the extended algebra. And then it's again enough to compute finitely many correlation functions to determine the theory completely. And such theories then always also have the property that the values of C and H are rational, and they are called rational conformal field theories. There are partial results on classification and explicit computations of correlators in many examples. And then there are also thoughts how this might help one to deal with non-rational conformal field theories. For example, the rational numbers are dense within the real numbers, and it is then believed that rational conformal field theories lie somehow dense within all conformal field theories and might be used to approximate them. But this is kind of an open research program. Now, back to things that are more directly useful for us and more down to earth. I would like to finish the part on conformal field theory to talk about partition functions. Let's first review the concept in general, the partition function in statistical mechanics. And here I take specifically the so-called canonical partition function, which refers to a particular kind of statistical ensemble, is obtained by taking the trace over the Hilbert space of states of the exponential of the Hamilton operator multiplied by minus beta, where beta is the inverse temperature. We can then, in the basis of energy eigenstates for the Hilbert space, write this also as a sum over exponentials of eigenvalues of the Hamiltonian, that is of energies. And that is a sum over states. And that explains why the German name for partition function, which also gives rise to the letter Z that we use, is Zustandssumme, which means sum over states. So as we see here explicitly, what we are doing in a partition function is we take a sum over all possible states in the theory, weighted with the so-called Boltzmann factor, which is exponential of minus the energy times the inverse temperature. Now, this is statistical mechanics or quantum statistical mechanics. There's also a mapping of normal quantum mechanics to statistical mechanics by Wick rotation. So we can define a partition function in quantum mechanics by taking the trace of the unitary time evolution operator. And this is time evolution operator is the exponential of the Hamiltonian multiplied by minus I times the time difference by which we propagate the state forward. And then we can take the trace of this evolution operator. Writing it out explicitly, this is a sum over an orthonormal basis of the Hilbert space of the diagonal matrix elements of the time evolution operator. We can formally relate this to a quantum statistical partition function by going to imaginary time and interpreting imaginary time as the inverse temperature. For a particle, one also has a diagrammatical expression for the partition function, which I think I will show you on a drawing. And this will explain why this partition function, when we express it in terms of diagrams, is also called the one-loop partition function. So let me go to these drawings. So the idea is that we, in the spirit of Feynman rules, represent the propagation of a particle by a straight line. In quantum field theory, one often uses Feynman diagrams in momentum space, but here it's more intuitive to think of this as Feynman rules in position space. So a straight line represents the propagation of a particle from one point to the other. And the partition function is then formed by imposing that the initial and final state is the same and closing the straight line into a loop, which will of course depend on the proper time that the particle needs to propagate from one point to the other. Therefore, there's two types of partition functions. In the sense, there is a partition function which we get when we evaluate this for a finite amount of proper time, but we can also sum over all possible proper times, which in momentum space would correspond to integrating over all possible momenta, and then we have an integrated partition function. Good. And yeah, I think that's what I want to say about partition functions for particles. Now, let's consider this, how this changes if we consider closed strings. And let's just go with our graphical intuition. The propagation of a closed string is described by a cylinder. And by identifying initial and final state and closing this, thus performing a trace, we get a torus. But there's one additional feature, or there are additional features that we have when we consider partition functions for strings. First of all, apart from having a dependence of this partition function on the proper time or momentum of the particle propagating around this loop, we will also need to sum over all possible excited states of the string. And secondly, and this is what we will now analyze in more detail, for a cylinder, I have the option to twist it before I glue it together. So there's a further parameter apart from the proper time that it needs to propagate around this torus, which needs to be taken into account when I consider a partition function for a closed string. But back to the lecture slides. I think we were maybe somewhere here. No, sorry. Yeah, I think this is the page where we ended off. So, so we have now understood that for closed strings, the propagator is a cylinder. If you get a torus by periodic identification, and we also need to take into account that we can twist the one end of the cylinder before gluing together. And therefore, the Euclidean partition function is not only the trace over exponential of the Hamiltonian operator multiplied by minus the Euclidean time, but we can also add a piece proportional to the worldsheet momentum operator P. So this gives us two real parameters, T and S, which tell us T is intuitively the proper time by which the closed string propagates before it meets itself, and S is the amount by which I have twisted it. And we are working here originally on the cylinder, so the Hamiltonian is L plus L0 plus L0 bar, where these are the L0s computed on the cylinder. And the momentum operator is L minus L0 bar, again formed on the cylinder. Why do I stress here that it's important to remember this is on the cylinder and not in the complex plane? Well, let's consider what happens if we map from the cylinder to the complex plane. This is a conformal transformation, but the energy momentum tensor is not a conformal primary. And therefore, the transformation behavior between cylinder and the complex plane is modified, and if you do the computation, you find that this modification is a constant shift by the central charge divided by 24. This only affects, if we then again expand in lower modes, it only affects L0. So L0 cylinder and L0 on the plane differ by a shift minus C over 24, which we need to carry. Then usually we parameterize this a bit differently. So these parameters S and T, which are the shift along which generates the cylinder, and S, the twisting that we do before we glue together, are ensembled into the real and imaginary part of a complex parameter tau, also including some factors 2 pi. And it's also useful to introduce as a shorthand the complex variable Q, which is e to the minus 2 pi I tau. And then we can write down a partition function, which now depends on a complex parameter tau, which is traced over the Hilbert space of Q to the L0, and if in Q bar to the L0 bar. And if we do it on the plane, we also have a certain shift proportional to C over 24. By the way, here you will see that I have allowed C bar to be independent of C. This is a generalization that one can make. One can define conformal field series by combining chiral sectors with each other, which are not complex conjugates of each other, but differently. And this is in fact the construction underlying the so-called heterotic string. However, for the construction that we are using in this course, C and C bar will be the same. Now let's find an interpretation for this parameter tau. And for this, it will again be useful to do this with a drawing, which I think is here. Another way of thinking about a torus is the following. We can cut the torus along the two independent non-contractible circles that I've drawn in this picture here and flatten it out in the complex plane, and then it becomes a parallelogram. And this can be used to to explicitly identify the parameter tau. First of all, we note that we are in a framework where we have conformal invariance. Therefore, the size of this torus does not play a role. So we can fix it to a convenient size. And therefore, I've placed my parallelogram in such a way that one edge is at the origin. And then I have put this edge here as the position 1, which fixes the size of the torus. But what matters still, if we have conformal invariance, is the shape of the torus. This is precisely contained by this edge, and this then is a complex parameter tau, which parameterizes the different shapes, or more formally, the different conformal structures that a torus can have. This parameter naturally lies in the upper half plane. If you put it on the real axis, then we don't have a torus because it degenerates. And putting tau in the lower half plane just gives us mirror images of the parallelograms that we also have. By the way, this flipping would correspond to changing the orientation of the torus, but we fix a conformal structure on the torus, and as we discussed, a conformal structure on the torus is the same as a complex structure on the torus, and a complex structure fixes an orientation. So we should restrict ourselves to having a tau, which moves around in the upper half plane, and this way we can certainly capture all conformally inequivalent tori. However, if we would do this, this would be a bit of an overcounting, because there's an additional symmetry called modular invariance. To illustrate this, look at the blue parallelograms here. Where the left blue parallelogram has edges 0, 1, tau, and tau plus 1. Now suppose I would make a large change of tau, which maps tau to tau plus 1. This would give me the red parallelogram. But it's completely clear that I could cut this red parallelogram and paste it back onto the original blue parallelogram. And this tells me that the blue and the red parallelogram are different as parallelograms, but they are different cuttings, if you like, of the same torus. So they represent the same torus, and therefore I need to identify the values tau and tau plus 1 if I only want to count every conformally inequivalent torus once. This is transformation, which is called T. And there are further such transformations, which just give different ways to cut torus into a parallelogram, and they form a group called SL2Z. So that's a group of unimodular or determinant 1 2x2 matrices with integer coefficients. This is a discrete group and is created by just two transformations. And apart from T, the only other one, often called S, is tau goes to -1 over tau. Now, what does tau goes to -1 over tau do? Well, if we neglect the minus sign, what this transformation is, it is the reflection on the unit circle. So if I have a point inside the unit circle, it will map it to a point outside the unit circle. However, it will also map the upper to the lower half plane, and that's why we have a minus sign, because this maps it back to a point in the upper half plane. It can be shown as standard results that you find in books on modular forms, that these two transformations generate the so-called modular group SL2Z. Okay, some fine print. So the transformation SL2Z, general SL2Z transformation acts as a fractional linear transformation, as is shown here, where the coefficients A, B, C, D are elements of an SL2Z group. By the way, if you look at it, you will see that if I take the identity A and D equals 1, B, C equals 0, and minus the identity, I get both times the identity on tau. Therefore, more generally, any SL2Z matrix gives the same fractional linear transformation as minus the same SL2Z matrix. Therefore, the actual modular group is what one calls PSL, the projective version of the group SL2Z, where we identify any two matrices which differ by an overall sign. Now, since we know that the two transformations which generate this group are the one which I gave on the previous drawing, we know that any point in the upper half plane can be mapped to a point in a fundamental domain. And then the points in the fundamental domain are in one-to-one correspondence with a conformally inequivalent tori. The standard choice for a fundamental domain has been indicated here. So remember, the first transformation is a shift in the real part by 1 unit. And then here in blue, I've given you a strip of length 1. And the most convenient choice is a strip between -0.5 and 0.5. And then I have this reflection as a unit circle, which I can use to map every point inside the unit circle to a point outside the unit circle, which I then can shift also into the blue strip. And this gives the resulting fundamental domain, which is the strip with the unit circle cut out. Okay, good. I think that ends my drawings here, and we can go back to the lecture slides. Here, I think we have this slide. Yeah, so here I give you in words what I explained in more details in the pictures, namely how a parallelogram is defined by identifying in the complex plane any points which differ by a shift by either 1 or tau. And then tau is subject to these modular transformations. Modular invariance of the torus partition function is a natural requirement that we can put on any conformal field theory, and is very restrictive. But it's natural because it says that the theory should make sense if I put it on a torus. And why is this natural? Well, conformal field theories in 1+1 dimensions, which we have mapped to conformal field theories in the Euclidean 0+2 dimensions, describe the equilibrium or critical behavior of statistical mechanics systems at second-order phase transitions. These are then systems which live on surfaces, and what we are requiring here is that we can take not just special but arbitrary surfaces and still have a conformal field theory which we expect to have when there is a second-order phase transition. So remember, second-order phase transitions are those phase transitions where the correlation length diverges and the theory loses all information about scale, so it becomes scale and generically conformally invariant. That's why conformal field theories describe in a field theoretic setting second-order phase transitions. In string theory, it's even mandatory, clearly mandatory, that we impose modular invariance because it is just part of the reparametrization invariance of the worldsheet theory. And yeah, if we want to talk about string theory processes where we also have worldsheet histories which include closed loops, like, for example, a torus with some legs sticking out, then we will need to impose modular invariance. There's no way out of it, so we will require this. Now let's do something explicit. Let us compute a partition function. We compute the partition function for one single string coordinate, or equivalently for one free massless scalar field. That means that we look at the Hilbert space of the chiral primary phi, which is the derivative of x, as we discussed. For simplicity, I just compute the so-called chiral partition function, which means that I only include q and not q bar. Now, the anti-chiral sector can then simply be added because it is an analogous computation. So I have to take the trace of this operator over the Hilbert space, and trace means sum over an orthonormal basis. So we remember that the Fock space is generated by some mode operators alpha m, which have certain commutation relations. We have a ground state which is annihilated by the alpha m's for m not negative. We normalize the ground state to have unit norm. Then we can form a basis by applying any possible number or combinations of operators alpha -1, alpha -2, so all the possible creation operators, and each creation operators can be applied once or twice or thrice and so on. So the basis states are then labeled by the occupation numbers n1, n2, and 3, which tell us how many times we have applied a certain creation operator. These states are then automatically orthogonal, but don't have automatically unit norm. So I need to include a normalization factor, which, like for the harmonic oscillator, I can compute explicitly if I like. But for the following computation, I don't need to know this normalization coefficient explicitly. I only know that I can. I only need to know that I can also normalize, so that then the scalar product between any two such basis states is one if I take the scalar product between a basis state in itself and 0 otherwise, so that I have an orthonormal basis. That's all I need to do my computation of the trace. You also remember the operator L0 can be decomposed into the zero mode piece alpha 0 squared, where alpha 0 is proportional to the momentum operator, and then they have this additional piece. And one can compute, maybe you have already done this, maybe not. At some point you should check this explicitly. It has this commutation, zero has this commutation relation with the alphas. And this is something that we have seen, or which follows from things that we have discussed. Our basis states are L0 eigenstates, and we can also compute what the eigenvalue is. Maybe this one here. Well, that's all we need for our computation. So Carrel partition function, we need to sum over all basis states. So we need to sum over all these occupation numbers n1, n2, and so on from 0 to infinity independently. And the operator for which we take the diagonal matrix element is q to the L0 minus c over 24. We now set c equals to 1. The factor q to the minus 1 over 24 I can pull out. And then these are L0 eigenstates, so I can evaluate the matrix element and get this expression here. Now, this is in the exponent, so I can pull down the sum that becomes a product, and then I pull the product through the sums, and then get a product of infinite sums, and each of these sums by itself is a geometric sum, which I can perform, and which converges if only the modulus of q is smaller than 1, which means that tau is in the upper half plane. And now I need to know something about special functions, or more concretely about so-called modular forms, for which we now imagine we open up the mathematics book and identify this function and learn about its properties. And then what we will find is that z is the inverse, or 1 over the so-called Dedekind eta function, which is one of these so-called modular forms. The fine print, it is a so-called modular form with multiplier system, because it transforms with some extra phases. The modular forms, to say it briefly, are just functions which transform as tensors under the modular group SL2Z. And eta does this almost, but only up to some phase factors. Modular forms are also required to have a certain behavior at tau goes to infinity or q goes to 0. Namely, they should not become singular at these points. Okay. Now we add in the anti-holomorphic sectors, and we get the partition function, or what could be the partition function for a string in 1 dimension. And this is a modulus squared of the Dedekind eta function to the minus 2. No, 1 over modulus squared of the Dedekind eta function. I was so insistent that this should be modular invariant. So is this invariant under modular transformations? We can use that the modular group is generated by these two transformations, so we only need to check these. For eta, shifting by the real part by 1, it is straightforward from the definition to see that this is invariant up to a phase. This is related why it is a modular form with a multiplier system. But for us here, this is not a problem, because in our partition function, we take the modulus anyway. So this phase doesn't bother us. But if you compute eta evaluated at -1 over tau and express it in terms of eta of tau, you get this prefactor here. And this causes a problem because it is not a phase, but depends on tau. To compute the S transformation is not as straightforward as for the T transformation. It requires special techniques, which you can also look up in books on modular forms. In particular, one needs the so-called Poisson transformation formula, which we don't have time to go over here. So we just state or read off from the book that this is a transformation behavior of the dedicated eta function under the S transformation. And if we put this in, then, as we already seen, tau goes to tau plus 1, partition function invariant. But for the S transformation, the partition function is not quite invariant. We have some factor of modulus tau sticking out. Now, what this means is that something is missing to make this into a modular invariant theory. And whenever a symmetry or something works almost but not quite, then we have forgotten something. So we should be able to add in some degree of freedom in order to make it modular invariant. Now, in our string theory application, it's plainly clear that we have forgotten something. And by remembering this, this will repair itself. Because what we have looked at is a Hilbert space associated with the conformal primary IDX and its complex conjugates. So what operators does it contain? Well, it contains the creation and annihilation operators alpha m and the momentum operator p, but it does not the derivative of x does not contain the operator x, which is the conjugate of p. But this means that we cannot create momentum eigenstates. All the states that we have considered are states with zero momentum, because in order to create non-trivial momentum eigenstates, I need to apply the exponential of the operator x. So that's it. Includes this in our Hilbert space. We remember how momentum eigenstates are constructed. Therefore, we now include them. We can also immediately check what applying q to the L0, q bar to the L0 bar, what this does on a momentum eigenstate. It gives something of the form exponential, some constant imaginary part of tau times k squared. Now, the trace means we have to sum over eigenvalues, but the momentum operator is a continuous spectrum. So the trace in this case is an integral, which is up to normalization, this integral here. We don't need to worry about the precise normalization, because the normalization of this integral will be a constant, but all that we care for is the tau2 dependence of this integral. The integral is a standard Gaussian integral, so it gives us something proportional to imaginary part of tau to the -1/2. And this is precisely what we need, because now you can check that this combination here is indeed modular invariant. Okay, so we have seen that we can construct a partition function for string propagating in one dimension, which is modular invariant, and by just taking more dimensions, we can also have a similar partition function, which is just the power of this partition function, which is then a modular invariant partition function for a closed string in d dimensions. This ends what I wanted to tell you about the worldsheet approach and conformal field theory. We now have all the tools available to carry out the covariant quantization program for the closed string. And since we have a few minutes left, we can already gently start by at least laying out what we have to do, and then continue with this in the next lecture. So how does the program work? We have decided that we want to work in a covariant, meaning Lorentz covariant quantization scheme. Therefore, we only impose a conformal gauge, which says that at least locally, our worldsheet metric is a flat metric. We keep space-time Lorentz invariance manifest. But we have to bear in mind that we have a residual worldsheet gauge symmetry, namely conformance symmetry. The construction proceeds in 3 steps. The first step is we represent our canonical commutation relations on some space F, which we call the Fock space. Then we impose the constraints, and this selects a subspace, namely the subspace of physical states. And finally, we have to identify any 2 physical states which differ by a null state, which corresponds to dividing out by the residual gauge transformations. And this gives us then the Hilbert space of states. What we then have to check, because this is not manifest, is that this space and finally has a positive definite scalar product. And turns out that this in general will not work, but only work if the number of dimension is fixed to 26. And we will also see that there is a certain shift in the ground state energy, a Casimir effect, which has to take a particular value in order for this to work. This is called the no-ghost theorem. A ghost refers to unwanted state of negative norm, which would destroy the unitarity of my theory. Still a few minutes left, so let's carry on. I think there seem to be no requests on the chat. Nobody's interrupting me, so I just carry on. Summarizing where we start from. So we'll be using string units, particular p times string tension is 1. We have our commutation relations. We have hermeticity, properties for our operators, and we have a ground state, which we now in conformal field theory language recognize as the SL2C vacuum, which is characterized by these properties here. First of all, we can construct momentum eigenstates. This is something that we have just seen. Therefore, I can be brief, but let me stress the following point. We now have to introduce a scalar product, and the natural scalar product for momentum eigenstates, because momentum takes continuous eigenvalues, is the delta function as a generalization of the Kronecker symbol. That reflects, of course, that momentum eigenstates, or if you do it in a more concrete description, plane waves, are not normalizable, and therefore they are not honest member of any Hilbert space. But normalizable states are then obtained by forming superpositions, or if you like, momentum space wave packets. So we take a continuous superposition of momentum eigenstates. The norm of such a state is then given by this integral, and we have to choose the profile of the function phi of k, which tells us to which strength a particular eigenstate contributes in such a way that the function is square integrable. Then we have normalizable states, and we can hope to get an honest Hilbert space out of this. But for many practical purposes, it's quite convenient to work with momentum eigenstates. This is a bit formal, but convenient for computations, because handling these wave packages is a bit messy. Then also, that would be, by the way, the same discussion we had for a point particle, but now for string, we also have oscillation states to deal with. So we form excited states by applying arbitrary chains of creation operators. Again, something that we have already seen today, but now let me stress one particular point, namely the scalar product is indefinite. As an example, we take this scalar product here between 2 states with one oscillator applied. We can unfold this and write this as in bracket notation like this. Then, because of the properties of these operators, we can write this as a commutator, which we evaluate and get this result. But this is necessary consequence of Lorentz invariance. We have eta mu nu here, which has positive and negative eigenvalues, and therefore our scalar product will necessarily be indefinite. That's not by itself a problem, because we only need that the Hilbert space that we ultimately create must be positive definite. Okay, so we are at step 1 of the procedure, and we have now seen what is the basis of our Hilbert space, Fock space F, we take momentum eigenstates and apply an arbitrary chain of creation operators on it. Good. Step number 2 is then the selection of the subspace of physical states. But now my alert has gone off. And therefore, I think, yeah, anyway, this is, I think, a good point to break. So let me stop sharing my screen and end the lecture for today. As usual, I stick around in case somebody has a question. Otherwise, the material on the Magic webpage is updated. So you should have you should now check your example sheet number 2 against my solutions, and you can read forward with part 5 if you like. So that's all for today. Looking forward to meeting all of you again next week. Bye now, and I'll hang around a bit in case somebody wants to chat.